Hey guys, BuildZoid here, and today we're going to be doing another AM5 motherboard PCB breakdown. This time it's the Asrock B650 LiveMixer board. I bought this motherboard, so big thank you to my patrons for making this video possible. And with that out of the way, let's get into it. So, I think we'll start with the internal connectors first. You get a PCIe Gen 5 M.2 slot that connects directly to the CPU. That's X4 Gen 5. You get a regular PCIe 4.0 X16 slot over here that's connected directly to the CPU. And then a pretty neat feature of this board is that you get this PCIe slot down here, which is PCIe 4.0 by 4, also connected directly to the CPU. So like ideal for like a capture card or something, because I have run into weird issues in the past with like capture cards going through the chipset, not necessarily, like sometimes it just causes weird software problems. So yeah, having a PCIe slot that just connects directly to the CPU is really convenient. And this PCIe slot doesn't affect your X16 slot because Ryzen does, like on a lot of other motherboards, this would actually be an M.2 slot, but ASRock decided to use it as a straight up PCIe slot. So I think that's really cool. That's sort of one of the main reasons that you would probably opt to go for this motherboard instead of some other board. Below that, we have an M.2 slot. This runs off of the chipset. It's PCIe 4.0 by 4. This M.2 slot is switched with this PCIe slot over here. You can it's probably this chip right over here that's handling that. So you can either have an M.2 drive here, or you can have another PCIe card in the bottom PCIe slot. You can't have both at the same time, as there just isn't enough bandwidth in the chipset for that. Now, this over here is just another M.2 slot running off of the chipset, and this one doesn't share bandwidth with anything, so you can just, like put a drive in that without really thinking about it. Now, one of the biggest downsides of this motherboard is the fact that it only has 2 SATA ports, which is a big problem for somebody like me, because like my personal system actually has like 3 SATA drives in it. But I think if you're doing a new build, this isn't really a problem, right? Like you've got 3 M.2 slots on the board, and if you know ahead of time that you're not going to have all of the SATA ports in the world, then you're just not going to buy a bunch of SATA drives. So, yeah, but that is something to sort of keep in mind with this motherboard, is just like it does have very limited SATA ports, even by B650 motherboard standards, because most other B650s would give you 4 SATA ports. Anyway, so that's sort of it for the... Oh, no, there's also the internal USB Type-C header over here, and that pretty much covers all of the sort of noteworthy connectors on this board. Oh, I guess you also have this M.2 slot. I'm not sure... It says M.2 Wi-Fi. I am not sure how that is implemented. I didn't really pay much attention to it. I kind of, like, the main reason I'm wondering about how that's implemented is, like, could you maybe stick an M.2 drive in that? And if you did, it would probably be tied, yeah, it would have to be tied to the chipset, because, like, the CPU PCIe lines are already used up by all of this over here, so this has to be connected to the chipset. I don't know what speed it's at. Probably not very high, because it's a Wi-Fi slot, but, or at least its intended purpose is a Wi-Fi card. Anyway, so let's move on to the rear I.O. For the rear I.O., you get a ton of USB Type-A ports, and unfortunately the orange really doesn't show up on the red, which is a bit of a shame. But yeah, you get a ton of USB Type-A. I'm a big fan of that. Like, I have a lot of USB Type-A devices, and they're not generally very fast. There's just a lot of them. So having a lot of, like USB 2.0 Type-A ports is convenient. Then you have the like ultra power USB stuff over here, which I think just means they have a dedicated 5-volt regulator for it, which is probably this right here. But yeah, so they have that. There's a Type-C port over here, 2.5 gig Realtek LAN, cut down audio section, which is something we see on a lot more boards these days, but you do still get the optical output. If you have like a external DAC that, you want to run off of optical, so sort of like prevent any possible interference or like grounding issues. That's a pretty handy port to have. And there's also a DisplayPort output and an HDMI output because, of course, all the Ryzen CPUs now have an iGPU built into the SoC. There's also a BIOS flashback button, which is a standard feature for AM5 motherboards as required by AMD themselves. And there's this little slot so that you can see there's a little LED that blinks when the BIOS flashback function is running. The main point of that is that if you don't have a compatible CPU for the board, you can update the BIOS without having a compatible CPU. It could could also theoretically recover from BIOS corruption, but that is not its intended purpose. And also, BIOS chips don't tend to go bad for no reason. That's not really a thing. So, though I guess if you did screw up a BIOS flash by like cutting the power as it's getting flashed, this might help you recover in that scenario, but that's not its intended purpose. Anyway, so let's go back to the inside of the board, the internal portion of the board. And, well, in terms of overclocking features, you get some troubleshooting LEDs, and that's it. And they're not color-coded, and they are right next to each other, so they're kind of a pain to read, but actually, it's not that bad, because Asrock has, like, some wacky, like, sequencing going on with these. So, like, what's typical of, say, a Gigabyte motherboard is that as the board boots up, it'll go, like, you know, CPU lights up, then DRAM lights up, then, boot device... Actually, I think VGA boot... Can't remember what the order is, but they'll just basically go through in order, and if something goes wrong, it'll just get stuck on whatever, initialization. It'll just, like, whichever part of the initialization process the system gets stuck on, that'll stay lit up. However, this board will actually, like, blink the DRAM LED as it's going through memory training, so you actually get a bit more information out of this than the usual just like, oh, this is the thing it got stuck on. Like, you can sort of see what, like, if it's actually doing something, which is kind of neat. I still wish these were color-coded, but the fact that, like, you get, like you won't have just one LED light up at a time is kind of an interesting approach to the, like, one LED being, like, one single-colored LEDs being kind of a pain to read. But I would prefer to see a postcode, but at this price point, that's just not happening. This is not a particularly expensive board, and all motherboard manufacturers have collectively decided that postcodes are a premium feature now, so yeah, if you're not paying more than like $300, you're not getting one, which really sucks, but there's really nothing that can be done about that. Anyway, so I guess let's move on to the power delivery, because, yeah, other than that, oh, I guess there is a clear CMOS jumper right there. If you wanted to, you could wire that up to your case's reset button, so that, you know, if you're doing a lot of memory overclocking, you can just use that. I would recommend it. Like, technically, AMD CPUs are supposed to have their own safe boot system so that if they detect too many boot failures, they'll recover from that. In my experience, that doesn't tend to work that often, and in that scenario, you're going to want to have you're going to want to hit the clear CMOS. So, yeah, wiring up your reset button to this, especially if you're doing a lot of memory overclocking, is generally a good idea, because AMD's safe boot is anything but reliable. Like, on some AGSA versions, it's actually really good. On some other AGSAs, it just doesn't work at all. So, relying on it, in my opinion, is not a reliable way of going about things, because you're eventually going to have to open up the system and reach for the clear CMOS jumper anyway. At least it's in a relatively convenient location, so that's nice. Now then, let's talk about the power delivery. You do get two 8-pin power connectors on this motherboard. You'd only need to plug in one of them, as currently there are 0 7000 series. Like, there is no CPU that you can put into this socket right now that'll max out a single 8-pin power connector. It's just not happening. So, actually, like, also, it doesn't matter which one you plug in. Like, these are dumb power connectors. They're just, like, one side is 12-volt connections, one side is ground connections. There's no fancy sensing, detection, whatever. Like, just plug in one of your 8 pins. Yeah, like, if you don't have a second 8-pin on your power supply, don't worry about it. It doesn't make a difference. Motherboard manufacturers put 2 8-pins on their motherboards mostly because it, like, looks more impressive. Especially on a board like this. Like, I can kind of get it if they do it on, like, an extreme overclocking board, but this is, like, a sort of workstation motherboard, right? Like, the LiveMixer name is meant for, like, live streamers. Even if you're doing, like, CPU encoding, like, your 7950X is just not gonna pull enough power to max out a single 8-pin. It's just not happening. It's not, no. So, yeah, the second 8-pin really is there just to look impressive rather than to serve any practical purpose. And, oh, I guess since we're already on the topic of the power connectors, Asrock is using the high current variant of these. These are solid metal pins, they're not folded metal pins, so having 2 of them is even less necessary than if they used the folded metal pins. Not that the folded metal pins would have had much of an issue anyway, but, you know, you do get the, like, 2 of the high power connectors and, like, higher power connectors instead of just 1. Anyway, now let's talk about the actual power delivery for the CPU. So, Asrock has gone with a kind of interesting VRM layout, in my opinion, in the sense that they've kind of squeezed everything together under the VRM heatsinks, which is kind of neat. Kind of a good thing. Everything has cooling. Even things that really don't need cooling get cooling. And the configuration is that here we have the SoC power. Then the rest of this is, I guess I should have, now we don't need a V in front of that. The rest of this is V-Core. I'm going to put that over here. The yellow and red color scheme of this board is really screwing me over with the orange. The yellow is not too bad, but the red is just, yep, that doesn't work. Anyway, then down here we have VMISC. Oh, and we also have this minor regulator that I don't know what it does. It doesn't matter. It's probably like 1.8 volts or something. Anyway, so we have VMISC. Did I really want to put that there? I'll put it over here. I think I just removed my E. I did. So VMISC. So this powers like the VDDG voltage regulators inside the CPU. It really doesn't have to handle a lot of power. And this right here is VDDIO MEM, which powers the memory controller. And it's kind of an interesting, well, it's not, like, it's kind of similar to where Gigabyte likes to put it. Like, Gigabyte also likes to put it into sort of this area of the board. But yeah, Asrock has moved it, like, all the way to the V-Core VRM, which is interesting, because, like, I think Asus boards put it, like, over here. So yeah, motherboard manufacturers get quite creative with the location of the VDDIO regulator. This location to me kind of makes the most sense because they did manage to squeeze it under the VRM heatsink. Not that it needs it, it's just kind of like, oh, yeah, cool. Your VDDIO MEM VRM will... It actually probably won't run slightly cooler because I'm pretty sure the heat output of the other two voltage regulators next to it is going to heat it up, but even like through the heatsink, but more so than... Yeah, probably, but it doesn't matter. It's a low power rail. It's just kind of an interesting choice for Asrock to put it here. Anyway, so let's talk about the most important of these power rails, which is, of course, V-Core. Now, V-Core here is, as far as I can tell, a 7-phase. So, actually, I'm going to put that over here. So, as far as I can tell, it's a 7-phase, because there are no doublers on this motherboard, which is standard for motherboards these days to not bother with doublers. So, yeah, 7-phase as far as I can tell, controlled by this chip right over here, which is a Renesas RAA 229620, which is a popular voltage controller for AM5 motherboards in general. In the past, I would have said, like, high-end motherboards, but now it's like everybody has one of these. Yeah, like, so many boards have this controller. It seems to be running in a 7+2 phase configuration, so +2 for the SoC VRM. And for the power stages, oh, and actually, it is worth noting that every motherboard that I've seen with this controller so far has one issue, which is that the load line calibration is set incredibly aggressive. So, yeah, and the basic problem with this is basically the controller is set up to not... You can't set a lot of V-droop, which means if you're doing static overclocking, you just have a sort of... You have more undershoot than you'd really want to have if you had, like, a higher V-droop LLC option. So, yeah, but, like, that's not really, like, a problem of the controller itself. That's more of a problem of the configuration of the controller. It's just like, for some reason, every motherboard manufacturer that uses it just doesn't give you the option to increase the V-droop by a large enough amount to eliminate all undershoot in static overclocking scenarios. For PBO, it really doesn't matter, because the PBO system is actually, like, the whole reason the default load line is so aggressive is the PBO system. Like, the whole issue is that AMD's default load line setting is very aggressive. And so if you switch over to static overclocking, that starts getting in the way, and you don't have any LLC options that allow you to add enough V-droop that you can get rid of the undershoot. But yeah, the boost system actually has a way of sort of working around the undershoot, so that's why the default load line is so incredibly aggressive, but a bit annoying. Anyway, so that's the controller being used, and yeah, it's just like a standard controller. Like, you'll even see it on X67TE boards. So, that's kind of that. For the power stages, Asrock has opted to go with they're not Intersil anymore because they're owned by Renesas, but ISL part numbers are Intersil to me. So anyway, it's an ISL 99360. This is a 60 amp smart power stage. So integrated current monitoring, integrated temperature monitoring, integrated like overcurrent protection, over temperature protection, so some extra safety features. Though the main defining feature of a smart power stage is the integrated current monitoring, which is a bit more accurate than some of the other current monitoring schemes that exist for voltage regulators, like like inductor DC resistance sensing or low side MOSFET resistance-based current sensing. But anyway, so yeah, not a particularly impressive nominal current rating, right? Like compared to a lot of other boards on AM5, 60 amp smart power stages doesn't really sound like much. But the thing is, like, there is 14 of these, right? We have 2 of these in each phase. And, like, for comparison, if you go back a few years, even, like, HEDT boards would have, like, 8 phases of 60 amp power stages. So this is a very powerful VRM. And the ISL 99360s, as far as 60 amp power stages go, are some of the more, are very, very efficient. So in terms of, like, theoretical VRM, efficiency here, at 1.2 volts output voltage and a 500 kilohertz switching frequency, outputting 200 amps, which incidentally, 200 amps is more than the stock current limit of a 7950X. A bone stock 7950X has a current limit of 160 amps. So yeah, but you know, if this VRM, so basically the only way you're hitting 200 amps is if you manually overclock your 7950X, because on default behavior, it will never pull more than 160 amps. So anyway, but if you do manually overclock 200 amps, the VRM will only produce about 17 watts of heat, which is, you know, like spread over 14 power stages on an 8-layer PCB, right? Like this board uses an 8-layer PCB, which is very, like, pretty much standard for AM5 motherboards. Yeah, like this is, you don't need a VRM heatsink on this VRM. Like, even though, you know, this is not a particularly impressive nominal current rating, like, this is still massive overkill. Yeah, so this will not struggle with overclocking a 7950X or any other CPU that you can put into the socket. Probably even for the foreseeable, like, I would not be surprised if this VRM was overkill even for, like, CPUs that come out for AM5 in, like, 2 years from now. Because, like, this is a lot of power delivery, and it's on an 8-layer PCB, so the board is actually very capable of dissipating heat just on its own. The VRM heatsinks are just sort of a nice extra on top of that. Anyway, 300 amps output current, this VRM would only produce about 28 watts of heat. Now, at this point, the VRM heatsinks become a necessity. However, the only way you're hitting 300 amps on a 7000 series CPU is with, like, liquid nitrogen. And even then, I'm not entirely certain that you would hit 300 amps, because the funny thing about LN2 overclocking is that your current draw doesn't necessarily increase that much. The thing that really goes up with LN2 overclocking is your operating voltage, which does drastically increase your power consumption, but your current draw doesn't go up that much because the low temperatures reduce the leakage in the silicon, so the actual, like, so overall power consumption is up, but the current draw isn't necessarily increased as much as the power consumption does. So you might go from, like, 200 to 300 watts on ambient cooling to pulling, say, 600 watts on LN2, but at very, like, but most of that increase is going to be because you go from, like, 1.2 volts to, like, 1.4, 1.5, 1.6 volts maybe, and so you're not going to see that massive increase in current draw because you're at that much higher voltage. Anyway, so yeah, even for LN2 overclocking, like, I would not be worried about running this board on LN2 whatsoever. Like, it's just, like, that's the thing, is, like, with AM5, all of the boards are incredibly overkill. Even boards like this, which aren't, you know, particularly expensive. Well, I mean, it's not a cheap board, but if you compared, like, it's, like, in the grand scheme of AM5 motherboard prices, it's not an expensive one. Anyway, 400 amps output current, the VRM would only produce about 41 watts of heat. Yes, you do need a heatsink at this point. There's no real way you're ever going to pull that much current. At least, yeah, no, I don't think we'll ever see a CPU on the socket that'll pull 400 amps. And 500 amps, now we're purely in theoretical territory, 57 watts of heat. Now, this is a major, like, at this point, you need, like, active cooling on the VRM, like, pointing a fan at it, that kind of thing. But you're never going to hit this, right? Like, this is just not going to happen. So, in typical AM5 motherboard fashion, when it comes to providing current to the, well, any CPU that you can put into the socket, this board, like pretty much any other AM5 motherboard, will not struggle whatsoever. So, yeah, like, very overkill, as is the norm for AM5 boards. So that's the vCore VRM in terms of current handling capability. The SoC VRM is pretty much more of the same, as Asrock opted to just use 2 more ISL 99360s in the SoC VRM, and these should be 2 separate phases, though I've not verified that. I'm just pretty sure that they should be 2 separate phases. Anyway, that's also like massive overkill. The SoC, the SoC power rail pulls even less power on Ryzen 7000 than it did on Ryzen 5000, though now we do have an iGPU. And I guess in the future, we might see some APUs that might actually put some load on the SoC VRM, but as it is right now, yeah, this is just massive overkill for any CPU that you can put into the socket. The vMISC rail is another ISL 99360, so more overkill. The vMISC rail literally primarily just powers some voltage regulators built into the chip that handle the power supply for the Infinity fabric. So yeah, like this is like there are like honestly, this is still a rather fancy vMISC voltage regulator implementation, because like this is a Renaissance. This is like a slightly scaled down version of what Gigabyte's doing on a lot of their boards. This is an RAA, and by slightly scaled down version, I mean they replaced the 90 amp power stage with a 60 amp power stage. So. But anyway, this is an RAA 2296 21, and like a 60 amp power stage on vMISC is massive overkill. There are boards where, you know, you'll get like an integrated 30 amp buck converter, as in the controller and the like power MOSFETs are built into one chip. So yeah, this right here is still just unnecessarily elaborate for a vMISC power delivery system, but that's kind of the norm with AM5. And then we get to VDDIO MEM. And VDDIO MEM, I don't have to say, oh, it's massive overkill, because it isn't. VDDIO MEM actually makes sense. You get one high-side MOSFET, one low-side MOSFET. Both of them are Sinopower SM 4337s. These are not good, these are not particularly amazing MOSFETs. They have like 7 milliohms of RDS on if you drive them with 12 volts, which they don't because they run off of a 5 volt power rail, so they're driven with like 5 volts, at which point they have like 10 milliohms of RDS on, which would be a problem if it wasn't for the fact that they only have to power the memory controller. This really isn't that different from like the VRM that you would see for the entire DDR4 power delivery system, and a DDR4 VRM had to power the memory sticks and the memory controller. This literally only powers the memory controller. So yeah, like, and Asrock even managed to squeeze it in under the heatsink. Like, you know, these are not like, if these MOSFETs were in the vCore VRM, I'd be complaining about how they're garbage and terrible and should avoid the board. But this is VDDIO MEM. We don't need fancy MOSFETs for this. And so this configuration from Asrock here is very, like, makes perfect sense. I have no complaints whatsoever. The controller and driver for these is an APW 8828 from Anpec Electronics, who are a sort of common supplier of like single phase power delivery stuff, basically. Both integrated buck converters to like controller plus controller and driver chips like what we have here. So yeah, like you normally see Anpec used on a lot of GPUs, more often than motherboards. So I was kind of surprised to see an Anpec part on a motherboard, but other than that, very, very like typical manufacturer for power, like basic power delivery stuff, for, you know, like computer hardware. So anyway, yeah, in terms of power handling capabilities here, we've got vCore, which is massive overkill, as is the norm for AM5. Then we've got SoC, which is massive overkill, as is the norm for AM5. Then we've got vMISC, which arguably more overkill than the SoC rail, as is norm for AM5. And then we've got the VDDIO MEM VRM, which is actually sensible. because yeah, like it's a good thing. I really have no complaints here. So, um, yeah, in terms of like MOSFETs used, controllers used, this is as good as any high-end AM5 motherboard. Like if you're thinking, oh, I'm not going to buy this board because it won't power my 7950X when I'm, video encoding on it, like doing CPU-based video encoding or whatever. Nah, it'll power your 7950X just fine. It'll power it probably even if you take off the VRM heatsinks and overclock, because the funny thing with the 7950X is because the IHS is so incredibly thick and the thermal density of the chip is so very high, it's very, very hard to get a 7950X to pull a significant amount of current because it gets incredibly hot, incredibly fast. So, yeah, like you're going to have major CPU cooling issues before VRM thermals become before VRM thermals on this board become a concern. So, yeah, pretty typical AM5 motherboard things there. Now, let's talk a little bit about the output filtering configuration, where Asrock has done something I find kind of interesting. Well, it's relatively standard Asrock motherboard things, but I find it kind of interesting compared to, like, as a contrast to, say, Gigabyte boards. There is a lot of, actually, even compared to other manufacturers. So the first thing I find interesting about this VRM on this board is that Asrock decided to use FP 12K Nichicon capacitors for all of the output filtering. So yeah, these are Nichicons. They're black, which makes it very obvious, though you can get FP12K. Actually, I'm pretty sure the FP12K label is like custom for Asrock, because I've not seen it as like I can just buy FP12Ks direct, like at least not on any like third-party supplier like DigiKey or something. But anyway, FP12K, 560 microfarads each, and these are 6.3 volt capacitors, which is, exactly the kind of bulk capacitance that you would expect to see on a vCore VRM of an AM5 motherboard, or really any high-end motherboard released in the last several years. However, what's interesting is that we have these FP12Ks on the output of the output filtering of the vCore, SoC VRM, VDDIO MEM. VDDIO MEM also has one for input filtering, but that's just because VDDIO MEM runs off of the 5-volt power rail, so it's like, well, we are already using all of these 6.3 volt capacitors anyway, let's just slap another one over here to, like, for the input filtering as well. Though interestingly enough, over here we have 6.3 volt capacitors from APAC. So I'm kind of like surprised we don't see one of those. I guess the logic is that like this area gets hotter. No, that doesn't make sense. The hottest part of the board is going to be like this area. But anyway, for input filtering, and this is the interesting part, they opted to use these bulk capacitors instead. And these are from APAC, a Taiwanese capacitor manufacturer, extremely popular on your, I guess, budget motherboards, or like budget to mid-range motherboards, or even low-end boards. Yeah, these are 5,000 hours. They're through-hole, like these are all through-hole aluminum polymers. And I just find it kind of interesting that this is like, because this is very uncommon, that you'll see a motherboard where they have like two different endurance ratings on the capacitors, because we have these 12,000 hour rated capacitors on the output of the VRM, and then the 5,000 hour rated capacitors on the input of the VRM. Not that it really makes much of a difference. Like the thing is, like, this VRM is so overkill that these capacitors really won't be running very hot at all. Yeah, interesting choice. Also, aluminum polymers, even if you run them really hot for a long time, they don't have they don't really have catastrophic failure modes unless you install them backwards, which they didn't because they're not ASUS. Anyway, but yeah, so I just find that kind of interesting that you don't see this more often from motherboard manufacturers, especially because like Asrock with these has the advantage that they're actually covered up by the VRM heatsink. So you can't even see them in most of the product photos for this board. And the only way you would notice the fact that like, hey, some of these capacitors are 5,000 hours, and the like vCore, like the actual output filtering for the CPU, those are 12,000 hours. It's like you see that like elsewhere on the board. I don't really think it's a significant difference, though Asrock is using the 12,000 hour rated capacitors as like a marketing point for like the reliability of the power delivery on this board. I really don't think it's relevant. Like, yeah, in my experience, like the only way you're really getting polymers to fail is if you like apply way too much voltage or install them backwards. That's about it. They are incredibly resilient. That's like their main advantage over, liquid electrolyte capacitors, is that they just kind of last forever and you don't really need to worry about them. But anyway, so yeah, Asrock wanted an extra like reliability marketing point, so they slapped some 12,000 hour rated capacitors on the output of the VRM. Though what I find more interesting sort of from the filtering perspective of like voltage regulation, there's a lot of these. There's 12. Yeah, which is a lot of output filtering capacitance for a motherboard. Unfortunately, like I've done oscilloscope measurements of this board. Unfortunately, this doesn't really seem to achieve much. We also have these little multi-layer ceramics mixed in between. I don't know what the capacitance on those is. These are actually a pretty standard thing. You'd usually, like Gigabyte likes to put those on like the back of the board. Yeah. So the output filter is kind of it's just interesting that they've opted for these more expensive Nichicon capacitors on the output. Not that I think they really do anything. Like these capacitors are not a good reason to buy the board. It's just kind of like, interesting that like this is one of the only boards that I can think of where you have like two different brands of capacitors being like used very intentionally, instead of it just being kind of a like, oh well, like it's not rare that you'll see like different capacitors used because of like supply constraints. But when it's like, no, we have these 12,000 hour capacitors and we're advertising them, and then we have 5,000 hour capacitors for literally everything else, is like, oh, that's new. Haven't seen that before. I don't really think it's significant, just kind of interesting. Anyway, for input filtering, you also have these multi-layer ceramics on the back. Oh, I guess I should have mentioned that the input filtering on this board isn't super substantial and a bit weird. Well, a bit ASRock is the better way to put it. So you do have all of these like multi-layer ceramics directly behind the power stages. This is standard practice. Like, this is good. This is what you want to see. For the bulk capacitance for input filtering, like 4 270 microfarad polymers, it's not the least that I've ever seen on a motherboard. At the same time, it's not the most. It's fine though, like input filtering isn't really, especially on motherboards, is just not that important. But what I do find most interesting about ASRock's approach to input filtering is that compared to most other motherboard manufacturers, they do not bother with input filtering inductors. It's pretty typical that on most motherboards, right after the power connectors, you'll have an inductor like here, or just like somewhere near the power connectors. And that inductor basically connects to the actual like 12-volt power plane that goes to the power stages. So like power comes in through the 8 pins, then it goes through an inductor, and then it gets to the power stages. ASRock doesn't do that for whatever reason. It saves them some money. Inductors aren't exactly the cheapest components, especially amongst passive components, like high current inductors are quite expensive. Yeah, like and it's not uncommon to see like low-end motherboards skip the input filtering inductor, but like this is not, like I've seen ASRock skip the input filtering inductor even on their like top-of-the-line motherboards. There's really no downside to it. But yeah, it's an interesting design choice, because literally everybody else always has an input filtering inductor, and then there's ASRock where they don't. Which arguably might put a bit more stress on the power supply, except like the power cables themselves, because they're very long, have some amount of inductance on their own. So that might be why ASRock decided that actually they're just not going to bother with input filtering inductors anywhere. So yeah, that's like the input filtering configuration is kind of interesting. I've already mentioned that the output filtering has a ton of bulk capacitance compared to a lot of other AM5 motherboards. But what I found especially interesting and annoying is ASRock's capacitor configuration directly behind the socket, because this silk screen right here, so this inner square, that is the standard cutout for an AM5 backplate. And for whatever reason, ASRock decided that that's just not enough space for all of the filtering capacitors that they wanted. And so they have custom, like their backplate has this larger, like raised section that nobody else uses, which was very annoying when I was taking the oscilloscope measurements, because like for Asus and Gigabyte boards, I just use like you just have like there's a backplate that just has a completely open cutout for like the inner section of this, and you can just use that. But if you try to use one of those backplates on an AM5 Asrock board, you can't, because like you'll crush this capacitor and that one and this one and probably these ones as well, and that would be very bad. So yeah, that I find very interesting, that Asrock wasn't like happy with how much space AMD has as like standard for the like filtering for the CPU, especially considering that the oscilloscope measurements that I took for this board weren't really that impressive. Like, it doesn't measure significantly better than any of the other motherboards that I tested. It's actually straight up worse than the Asus Crosshair X670 Gene board. So, yeah, I'm not sure why they didn't just use the standard, like, why they weren't satisfied with just the default config, like default opening in the backplate for the filtering for the CPU. It's also kind of interesting that ASRock opted to use 0603 capacitors, whereas most other manufacturers, actually, are these 0603s? I think they're 0603s. Yeah, these are 0805s. So most other manufacturers will just smash like a bunch of 0805s back here. ASRock opted for 0603s. The like idea for maybe doing that is that 0603s do have a lower ESL and potentially a slightly lower ESR. However, again, based on measurements, it really didn't seem to do anything. Asus boards, which just go with a ton of 0805s, generally perform a little bit, like, well, depending on which Asus board you measure, either a little bit better or a lot better. So, yeah, interesting choice by ASRock. Like that, yeah. This is just like, to me, interesting. I find it very interesting. So anyway, then we've got some extra multi-layer ceramics over here for the SoC rail, which also not something I can say I've seen on a lot of other boards. I mean, Asus likes to smash a bunch of multi-layer ceramics right up against the CPU socket. They have like some over here for V-Core and here. But yeah, ASRock has like a bunch of multi-layer ceramics directly on the output of the VRM. And the thing about this is this probably isn't that effective, because the further away your multi-layer ceramics are from the CPU, the less impact they have. Because the whole benefit of the multi-layer ceramics is that they have a very low ESL and a low ESR. So the further, like, and you're negating a lot of that benefit by putting them further and further away from the thing you're trying to filter, which is, you know, the CPU, which is here, not there. Similar situation with VDDIO MEM. I have no idea what this is for. Like, the VDDIO MEM power rail is not a very significant power rail. This is very elaborate for that. But yeah, the bulk capacitance is like that is not weird, but the extra ceramics that ASRock has gone with, that is interesting. I've not noticed any like overclocking differences on this board versus other boards. In terms of like infinity fabric, memory clock, anything like that. Like, yeah, so, yeah, I find it, and admittedly, I haven't taken oscilloscope measurements of the SoC rail and the VDDIO MEM, but the reason I don't do that is in the past, I have taken measurements of the SoC rail, and there's just nothing to see. It's a straight line. So, yeah, and I don't think Ryzen 7000 changed anything there. There's also like a tantalum polymer here. I guess maybe this is provisioning for like more powerful iGPUs in the future, because GPUs are very noisy. GPU power delivery compared to like CPUs is way more difficult. So maybe that's why ASRock has all this extra ceramic for the SoC rail. But for VDDIO MEM, I just have no idea what that's supposed to do. Like, it's the memory controller. That it's like, it doesn't pull any power. Why does it need almost as much, you know, like as many multi-layer ceramics as like your SoC rail? I have no idea. Anyway, so that's the filtering on this board, and like it looks really elaborate, which is actually sort of the main reason why I actually bought this board. Is I really wanted to like, I bought this board because, one, I wanted to see how ASRock's BIOS handles memory overclocking, that kind of thing. I also wanted to see if like ASRock came up with some better power delivery solution for Ryzen 7000, because in the past, like on AM4, the B550 Steel Legend had incredible voltage regulation. Like, it did a really good job beating out motherboards that are significantly more expensive. This, on the other hand, is not doing that. This, like, it's not bad, but it's also not like amazing, which yeah, I was kind of hoping for more, considering that, you know, Asrock was like, oh, we don't have enough space for our filtering capacitors behind the CPU, so we need a backplate that doesn't fit any, like that, like we have a different size backplate from everybody else because of it, and it's just like, this doesn't seem to really achieve anything, but now your motherboard is like, if you have a heatsink that like needs to replace the backplate, this board's going to cause issues because of this and that. So yeah. Anyway, that's sort of my, yeah, so that covers my thoughts on the power delivery. Very, like, tons of current handling capability. Voltage regulation wise, nothing really that special. It's not bad, but it hasn't blown me away. And yeah, an interesting approach to the capacitor configuration, but the measurements that I have don't seem to indicate that it really achieves anything. Oh, and the V-MISC rail is also more just like Asrock seems to have just a lot of extra multi-layer ceramic capacitors spare because they are really just smashing them anywhere they can. So, I mean, that's a good thing. Multi-layer ceramics are good, like, are great for power filtering, but it's just like, I don't think this is actually making much of a difference. Anyway, let's move on to the memory topology. There's not really much to say about this. I've already mentioned this is an 8-layer PCB, which is pretty typical for any AM5 motherboard above $200. It is a daisy chain topology, as you can tell from the label right here on the board, so you're going to want to use this DIMM slot and this DIMM slot first. I've not noticed any significant difference in memory overclocking between this board and any of the other motherboards I've tested. So, yeah. It is a shielded daisy chain, right? You can't see any of the memory traces, and we do seem to just have a straight up like ground fill over the top layer. And then on the back of the board, same kind of situation. I mean, you can see the command address bus, right? That's these traces over here. But other than that, it's just great big ground fill over everything, which is typical of AM5 motherboards. This is just like they all look like this. So, well, except Asus boards. Asus boards have a slightly different approach, but actually, do they? I might be misremembering. The crosshair has a, well, the crosshair's on a, I think is it on? No, it's an 8-layer, so they could just hide it somewhere. Anyway, doesn't matter. Like, memory topology-wise, it's an 8-layer daisy chain. You can't see any of the data queue. It's about as standard as it gets for AM5 motherboards. So, yeah. No, like, oh no, there, oh, there. My spacebar got latched somehow. Anyway, so that covers my thoughts on the B650 LiveMixer. It's a good board. Like, I kind of wish I really wish there was more V-droop available on the VRM. But other than that, if you're not doing static overclocking, like this board doesn't have any real downsides, right? You have plenty of power delivery for any CPU that you can put into it. It has some pretty unique connectivity options. Watch out for the, lack of SATA ports if that's something you care about, or the low number of SATA ports, I should say. It still has them, but there's only 2, so... Anyway, yeah, but, like, it's just a sort of, like... AM5 is a bit boring. I gotta be honest, it's a bit boring. The boards are generally pretty expensive, but they're also all generally good, right? Because they're expensive. It's like, yeah, you can afford to have 1460 amp smart power stages on a board like this. Like, that's, you don't have to cut every corner when the board is that's the thing with AM5. They don't have to cut all the every corner that they could find, like they did with certain AM4 motherboards. Though I really wish this had a postcode, but there's a lot of AM5 motherboards that I could say that about. So, yeah, like at least the Ryzen memory controller isn't that like temperamental, so the postcode isn't that necessary. Anyway, yeah, so that's the B650 LiveMixer. Just a solid motherboard. If you, like, also the third reason that I went for this Asrock board instead of some other Asrock board is the color scheme. I like colors. I don't like RGB. And the reason I don't like RGB is most RGB implementations are basically colorful chicken pox, right? There's just LEDs strewn about the PCB and they change color. That's not a replacement for, like, anodized aluminum, as far as I'm concerned. Like, it's not the same. RGB does not replace just solid colors, as far as I'm concerned. So, yeah, anyway, but from an overclocking perspective, this is a perfectly good board. Really, the only complaint I have for it is, like, I wish it had a postcode, but it's not expensive, so it doesn't have a postcode. That's just how it works with modern motherboards these days. So, yeah, that's it. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And that's it for the video. So thanks for watching, and goodbye.